Text-to-speech or speech synthesis is the opposite of automatic speech recognition or ASR. Text-to-speech synthesis is the process of going from Unicode text to audio signal that sounds like a real human, but isn't. I'm going to cover this briefly, but I'm actually going to spend a little bit, perhaps more time on all the ways that speech synthesis doesn't work before going into what does work today. And these are based on an understanding of the various properties of speech. So the first one is articulatory synthesis. That's the attempt to model human articulators, how speech is produced in the mouth, lungs, and nasal cavity. That doesn't work. The second one is called format synthesis, which is bypassing human articulation and modeling those sound waves, the acoustics directly. So format is another term related to acoustics or meaning frequency or frequency bands. The final one, concatenative synthesis, is synthesizing speech by concatenating or putting together stored units of actual speech. And that one is the basis of what does work today, although perhaps not entirely successful by itself. Okay, so first of all, why don't we just record a voice saying certain phrases or words and then play them back in whatever order or context that's needed? Kind of like a talking doll that had a recording in it, and you might press its tummy, or Woody on Toy Story, pull the string, and he produces speech. The problem with that is it's too brittle, it's too limited. Speech synthesis needs to be able to generate whatever somebody's saying, and you can't predict ahead of time what somebody's going to say. So it needs to be able to work with any speech that's produced on the fly. And secondly, intonation is an important piece of information in speech. And if you just record a certain intonation, it may not be appropriate. You don't want to be talking with an excited intonation when you're responding to somebody with information about, say, directions to a funeral home. Probably giving somebody directions to a funeral home is not something you want to say with excited or happy intonation. So that's something that has to be solved that approach to speech synthesis cannot deal with. So articulatory synthesis was kind of the first attempt, and this is creating synthesizers that send instructions directly to articulators. So something mechanical that imitates the voice box, the tongue, the different parts of the tongue, the lips, and the movement of the jaw. And we'll see if this little clip will play. You may not have good enough playback for it to work for you, but I will post it on the Canvas site for you to watch it. This is displaying, it's an X-ray, displaying human articulators in action in a conversation between actually a Chinese speaker and a German speaker. Articulatory synthesis was not successful, is extremely hard. Trying to create a mechanical imitation of the very well-designed human body is very hard, and we don't fully understand how they all move and work together. They're very complex. So that was a fail. That didn't work. Also, it created some kind of spooky thing. So this is an attempt at an articulatory synthetic speech machine. You can see here, this bottle here presumably is imitating the lungs, producing the airflow from the lungs into what is apparently the mouth cavity, may have a tongue in there, and this, I assume, is the nasal cavity, speaking into a microphone. This didn't work very well, and I don't know about you, but I think walking into a university lab basement at night and seeing this thing staring at me would give me the creeps. So maybe it's good that it didn't work after all. The second attempt to build speech synthesis was called format synthesis. The idea here is, okay, articulatory mechanisms are hard to imitate. Let's go straight to imitating the sound waves that are produced by the mouth and lungs. So we'll come up with rules that can recreate these sound waves and generate an audio signal from them. They'll capture the change of acoustic features in speech over time as we understand them. And then we will perhaps adjust some of the parameters of those sound waves, make them smooth together to create a continuous or what looks like or sounds like a continuous speech and see if that works. So you could have a model of the voice, maybe whether it was deep or whether it's high, the style of speech, perhaps the intonation, the emotion, acoustics, then the sounds themselves as we understand them, as they are represented in the acoustic sound waves or oscillograms. Create the rules that will create them, tell the computer which is needed, produce them through some rules, add some parameters to smooth things out, make it sound more natural, and synthesize and get the speech. Well, sounds great. I mean, we know a lot about acoustic models, about sound waves. It's been studied for a while. So it was easier than articulatory synthesis, but it was still very hard and not successful. So finally, this attempt here, concatenative synthesis, is not completely successful, but it was successful enough to build a foundation and be somewhat integrated into modern speech synthesis. The idea here is we can take some recordings of speech. We can segment that speech into individual sound units. That could be phones, individual speech sounds, syllables, words, phrases, sentences, and things in between like diphones, so two sounds at a time. So this may sound similar if you remember about speech recognition, where you break them down or at least correspond those sounds in transcription to the units in the audio signal in order to train the computer to be able to know how to map the two things together. In this case, you'd also have to do that mapping or do that breaking down, and then you'd actually segment the individual sounds and the individual words and sentences into separate audio files. And then when you run into or are given some text, some Unicode text, use some sort of model that would tell you which of these samples are best to concatenate or kind of glue together into the speech sounds that are needed to represent that text. And then on top of that, it's going to sound very weird if you take cuts of this person speaking and that person speaking, of course. So some smoothing, some sophisticated engineering is needed to make it sound like a smooth speech. And then in order to fit it into the duration that's needed, you might have to stretch or compress the length of the audio. And of course, when you draw out audio and make it slower, it tends to become lower pitch. And when you speed it up, it gets very high. And so that also had to be engineered. And on top of that, you could add the change in fundamental frequency over the speech utterance to provide proper intonation and appropriate loudness for stress and etc. So this was a step in the right direction. So it's kind of the basis for what we use today. But I'm not going to go into any more detail. Let's just look here at generally how speech synthesis works today in a big picture. So first, the computer is given the text that needs to be synthesized into speech. Some lightweight text analysis is needed. For example, with context and some processing of the context, we need to be able to determine whether R-E-A-D should be pronounced as read, as in the present tense, or read in the past tense. So some analysis to help with those choices is done. And then the neural, or it's often called deep learning acoustic model, is run. So this is a training of being able to go from the text into concatenate the speech together and produce an appropriate speech sample or speech signal, which is further smoothed out. Sorry, this is where all the smoothing out, this is the model that's built. This is the point at which it goes from a um, a bunch of numbers in the computer that represent a waveform into actually being turned into audio. And that then is played out on someone's electronic device.